All right, welcome to lecture number 22. Today, in this first video, we're talking about the electric grid and specifically the history of it and how it works. In video number 2, we're going to talk about supply and demand in the electric grid, how we meet the demand with the supply of power plants. And number 3, we're going to talk about the unique influence of renewable energy on the electric grid. All right, so let's start with video number 1. So we have all types of energies that we've talked about, right? Solar energy, we'll say thermal energy for something like a Rankine cycle. We have nuclear energy, we've got tidal energy, geothermal, we've got wind, we've got all these different kinds that we could possibly use to generate really the kind of energy that's becoming the most prevalent in today's society, which is electrical energy, right? This is what a lot of us want and need in order for our lives to even function anymore. And we need to get that energy from these other sources. And the way we do that, this arrow represents a power generation site, whether that is a coal-fired power plant or a hydroelectric dam or a large field of photovoltaic panels, or even just the photovoltaic panels on someone's roof. These are power generation sites. And the problem is we need to get the energy from where it was, right, as blowing wind, as sunlight, as natural gas, and we need to get that energy as electricity to its end point, where you will convert it back into thermal energy. Okay, so that power that you're using, it's actually generated in real time. That means the energy I'm using right now to create this video is being converted right now at this very second as I use it. And that energy is brought to me using the grid, the electric grid. So let's talk a little bit about the electric grid. Okay, so on the left is this diagram, which I failed to cite my source, but I got it from, of course, Wikipedia. And this kind of shows a few different aspects of the grid. And I think the first point to understand is that as the voltage in the power lines goes up, then the amount of energy we lose as we transmit it from the power plant goes down. So as voltage goes up, transmission losses go down. So that means we have these extremely large power plants, like a coal power plant, a nuclear power plant, a hydroelectric plant. These are all connected to extra high voltage wires. I believe these voltages are specific to the UK, not necessarily the United States, as we'll see on the next slide. Okay, and we do this because these are generating a lot of power, which we usually need to move a long distance. So we pump that up to a really high voltage. It's not usually generated at that voltage here, but it's sent to a transformer plant, which pumps that electricity up to a higher voltage. That is then transported long distances. It can then be stepped down to a generally just high voltage tower, where smaller power plants are going to contribute energy into that grid. Then it enters, so this was the transmission grid, kind of the connected wires that collect all of the energy from the generation sites. It then enters the distribution grid, where that energy is now distributed to end users. This is at a low voltage. The power lines outside of your window right now are distribution grids, or 50 kilovolts power. So these are where smaller distribution sites, like a small city power plant, or a large factory, or even a solar farm or a wind farm, will be connected. And then, of course, this goes down. So these transport kind of to neighborhoods, which are then transformed at transformers down to the actual 110 volts, which goes into each house, or 220 volts. Yeah, so that's kind of how the grid works, a series of voltages, because we want to transmit that energy as effectively as possible. Okay, and like we said, the large power plants will utilize the highest voltage because they want to transmit a lot of energy. And then medium plants, say here, are going to utilize a smaller voltage. And then on the distribution part of the grid, you notice we still have some things generating power. These are usually things that are regionally located. So like solar panels need to be in the right place, just like wind turbines, so they connect into the most convenient grid, being the distribution grid. And this has the lowest voltage and therefore the greatest losses in transmission. Okay, now in the United States, here's a map of the United States, its transmission grid, and you see we have all these different colors which correspond to the actual kilovolts of the lines that transmits electricity everywhere. So you can see we kind of have these pockets of different voltages, right? So here's some voltage, here's a voltage, oh, here's a different voltage right here. And then we kind of just have this whole chunk that does whatever it wants. You'll see that these actually correspond to the regional management centers, which we'll show in a later slide. So there is kind of still the Wild West out there of what actual transmission voltages we're using, but it all works, right? The lights turn on. Okay, before we talk any more about the grid, let's talk about the history of the grid. It is a storied history. They just made a movie about it even. That's probably a very boring movie, but it exists. Okay, so in the earliest days, there were only microgrids. So the generation, usually kind of smaller generation plants, was located close to the load. Remember we talked about, was it Thomas Edison's first power plant was in downtown New York City, where they undoubtedly do not have them anymore. As an important note, the voltages varied significantly. So if you had a motor, it used several hundred volts. Thomas Edison's newfangled light bulb used 110 volts. There were arc lamps for street lighting that used thousands of volts. I mean, there was a different voltage for almost everything, which is why in this picture of New York in, I believe it's about 1890, we see thousands of different wires, given some of these are telegraph wires, but still a lot of these would be different voltages corresponding to different machines, different items needing different voltages, and it's just very, very messy. And so because it was messy, we transitioned to centralized distribution, centralized generation, distribution, and billing. So the business structure of utilities quickly adopted kind of this vertical structure where they went from generating the item, the energy, transmitting that energy, and then billing you for that energy, which for a lot of other things, like things you buy at Walmart, you see that's those different parts are owned by different companies. Okay, and this actually happened because of the gaslighting industry, which also followed this very similar business model. So it's really because of gaslighting that we have the utilities the way we do now. Okay, then there's of course the story of Thomas Edison, who believed in direct current and sold direct current power plants throughout the United States. And then Westinghouse, who initially worked with Edison, but then realized that alternating current might be more advantageous. And so they go across the country competing for market share. Until finally at the World Fair in the late 1800s, I believe it was, that Westinghouse wins the contract to install AC to showcase to the world the power of alternating current, and he ultimately won the debate. And the real reason he won is because the conversion of alternating current voltages is actually relatively inexpensive. It doesn't take very complicated machinery, something like a transformer. However, for DC converting different voltages, it's actually fairly expensive because it takes more sophisticated equipment. It's really this reason right here that Westinghouse won the battle, because alternating current is easier to convert voltages to different values, which is really what they needed in the early days, since all these different items use different voltages. Okay, and this led to ultra centralized generation. Once we had alternating current and we kind of had a bit of a monopoly, then it made sense to make just a huge power plant and send that power at very large voltages, which we can convert to easily, out to the rest of the country. Okay, but let's talk about the grid today. Okay, so the grid today is an interesting animal. It is essentially regulated by the government, who has given permission to a nonprofit named the North American Electric Reliability Corporation, or NAERC. And these people are essentially in charge of the reliability of the grid. It is their responsibility to make sure there are no blackouts or brownouts when the voltage of the lines either goes to 0 or drops below significantly 110 volts. So it's separate from government, but a government appointed entity. Now the NAERC, they appoint regional entities or organizations that are responsible to ensure the reliability of a smaller grid. So for example, right here, you see, including Ohio, is the organization Reliability First, who manages the grid in this region and makes sure that it stays reliable, that the voltage and the hertz stay and the frequency stay exactly where they need to be. Okay. Now you're sold electricity from a local utility, which, as it turns out, has a monopoly. You really can't go buy electricity from a different producer and supplier. There's one grid and one person providing you energy from that grid. This is allowed by the government in order to increase the reliability of the grid. It's easier to manage the grid if one person owns it. And because, let's be honest, installing millions of miles of copper or aluminum, almost always aluminum wire, burying it in the ground takes a lot of money. It is an expensive infrastructure, and it makes more sense to just have one. Finally, as a really important note, we're pretty organized here in the United States, and early on we came to expect grid reliability. And what this means is it was something we knew we could build on. And in the end, now we don't just expect, we need grid reliability. The world would crash as we know it if the grid was not reliable. Okay, that's it for kind of the history of the grid. Next, we're going to talk about the demand on the grid and then how we supply that energy to the grid.